Have you ever watched a large delivery truck trying to make a tight turn onto a narrow street? The driver inches forward, then reverses a little, turning the steering wheel with great effort. It's a slow, careful dance of metal and rubber. Will it clear the parked car? Will it scrape the curb? This everyday drama unfolds on city streets constantly. The truck needs a certain amount of space to maneuver. It cannot simply pivot on the spot like a spinning top. This common sight is a perfect introduction to a hidden world governed by simple geometry. The truck driver is battling a fundamental constraint known as the minimum turning radius. It's the smallest circular path that a vehicle can make. Every vehicle has one, from the smallest scooter to the largest ship. Understanding this concept opens our eyes to how it shapes the design of everything that moves. Think about that truck again. Its long body makes sharp turns difficult. The front wheels can only turn so far. If they turned too sharply, the truck might become unstable or parts might collide. Designers calculate the tightest turn a truck can safely make. This calculation is a physical limit, dictating where the truck can and cannot go. This simple fact has big consequences for logistics and city planning. So the next time you see a vehicle struggling with a turn, remember this. You are witnessing a fundamental principle in action. It's not just about driver skill. It's about the inherent design of the vehicle. This idea of a minimum turning space is everywhere. It's in the curve of the roads we drive on. It's in the layout of the parking lots we use. It's even in the way a small child learns to steer a tricycle. Let's simplify things. Think about riding a bicycle. When you want to turn, you turn the handlebars. The sharper you turn the handlebars, the tighter your turn. But there's a limit. You can't turn the handlebars a full 90 degrees. If you did, the bike would likely tip over or the wheel might hit your foot. So, even a bicycle has a minimum turning circle. Now, consider a car. It's a bit more complex than a bicycle. A car has two front wheels that steer. When you turn the steering wheel, these front wheels pivot. They follow specific angles designed so the car turns smoothly. The inner wheel actually turns a bit more sharply than the outer wheel. This clever geometry helps prevent tires from skidding. The minimum turning radius of a car is the radius of the smallest circle the outer front wheel can trace. This minimum turning radius is a crucial specification. Imagine trying to make a U-turn on a narrow road. If your car's turning radius is too large, you won't make it in one go. Smaller cars generally have smaller turning radii, making them more agile in city traffic. Larger vehicles like SUVs and trucks have much larger turning radii. So the turning circle isn't just an abstract idea, it's a very practical measure of a vehicle's agility. Engineers spend a lot of time optimizing this. The next time you effortlessly steer your car around a corner, remember the careful calculations. It's all about that circle. The concept of the minimum turning radius is vital for urban planners and civil engineers. When they design our cities and towns, they think about how vehicles move. They need to ensure that roads are wide enough and intersections allow vehicles to turn safely. This is especially true for larger vehicles like fire trucks or buses. These essential vehicles need to reach every part of a city. Consider a simple road intersection. The corners are not usually sharp 90-degree angles. They are curved. This curve, known as a curb radius, is carefully designed. It must be large enough for common vehicles to turn without mounting the sidewalk. If the curb radius is too small, longer vehicles will struggle. They might hit the curb or swing into oncoming traffic lanes. Planners use standard turning radius data for various vehicle types to guide their designs. Roundabouts are another excellent example. They are designed to keep traffic flowing smoothly and safely. The central island and the entry and exit lanes are all shaped by turning radius considerations. The diameter of the central island must be large enough for vehicles, including large trucks and buses, to navigate the roundabout without difficulty. Emergency access is a critical factor in urban planning. Fire engines, ambulances, and police cars must be able to reach any location quickly. This means that even narrow residential streets or cul-de-sacs need to be designed with their turning capabilities in mind. Sometimes a cul-de-sac will have a large circular end. This allows these larger emergency vehicles to turn around easily. Without considering the turning radius, emergency response could be dangerously delayed. So, this geometric principle directly impacts public safety and the functionality of our communities. It's a basic but powerful piece of hidden math. Navigating tight spots, from parking garages to airport gates. Parking garages challenge us with tight turning circles. Engineers design ramps to maximize space, but they can't be too tight. Airplanes face similar challenges. Taxiways must accommodate large turning radii. Pushback tractors assist in tight spaces. From cars to jets, turning circles govern movement. Beyond the asphalt, turning circles in unexpected places. The importance of turning circles extends far beyond cars, trucks, and airplanes. Consider the world of robotics. In modern factories, robotic arms perform complex tasks. They weld, paint, and assemble products with incredible precision. These robots often operate in confined spaces, surrounded by other machinery. Each joint of the robotic arm has a range of motion. The combination of these movements defines the robot's workspace. It also dictates its ability to maneuver its hand or tool around obstacles. Engineers program these robots carefully, always mindful of their turning capabilities to avoid collisions. Even in agriculture, turning circles matter. Large farming equipment, like combine harvesters or tractors with long attachments, needs to turn at the end of each row in a field. The space left at the edge of the field, called a headland, must be wide enough to allow these machines to turn around efficiently. If the headland is too narrow, the farmer wastes time and fuel making multi-point turns. This can impact the overall productivity of the farm. So even the layout of a farmer's field is influenced by the turning geometry of machinery. Let's go to the water. Large ships, like container vessels or oil tankers, have immense turning circles. They can take several miles to complete a turn. Their sheer size and momentum mean they cannot change direction quickly. Harbor pilots, who guide these massive ships into port, must have an expert understanding of their turning characteristics. They often use tugboats to help nudge and pull the ship into tight berths. The design of harbors, channels, and docking areas must all account for these vast turning circles to ensure safe navigation. The need to turn efficiently is a universal aspect of movement. The unseen architect, the constant presence of turning geometry. The minimum turning radius is a fundamental geometric principle. It shapes our world in countless ways. From city layouts to vehicle designs, it influences efficiency and safety. A hidden math with tangible impacts. Appreciate the unseen geometry at play. The turning circle is an unsung hero of design.